Hello. Today we're going to be talking about nuclear physics, how nuclear reactors work, and we're going to talk a little bit about the relationship with the environment for one example where we've had a nuclear accident. So we'll start with how really does this work? And so I want to recall a few things from earlier in science where we talk about, the periodic table of elements. It may actually be useful for you to kind of have that with you while we look at things, but it describes the differences in what makes up different atoms. So you have protons, those are the positively charged part of the atom. You have electrons, negatively charged part of the atom. And they have the neutron, which is not positive or negative. It's neutral. Protons and neutrons exist within the nucleus, and electrons orbit, in a sense, around the nucleus. Now here's our periodic table. It describes the differences, and I'm going to be a little bit clear about this. So let's talk about a few atoms. We'll talk about hydrogen, has 1 proton. Helium, the next element, has 2 protons. Oxygen, 8 protons. Uranium, 92 protons. These elements also have the same amount of electrons respectively to their protons. Where things differ a little bit is the atomic mass. So this is telling us something about the neutrons for the atom. When we take the number of neutrons, or to find the number of neutrons, we actually take the atomic mass and subtract the number of protons. So the mass of hydrogen is 1. We take away 1 proton, we get 0. So there are no neutrons in the hydrogen atom. Judging by this information, you may be able to determine how many neutrons are in the helium atom. So we take 4, subtract 2, and we get that there are 2 neutrons in the helium atom. Oxygen, 16 minus 8 is 8, so there are 8 neutrons in an oxygen atom. And then finally, for uranium, 146. Now, this should be recall for everyone, but we're going to learn a little bit more. The elements we actually just described are the most stable versions of each atom. Now the proton indicates which atom we have, but the number of neutrons can vary. However, there is consequence with that. What this means is that even though oxygen has 8 neutrons, it can actually have more or less. The same with every element. Let's take a look at hydrogen. Hydrogen, as we previously saw, had no neutrons. Usually it has no neutrons, but it can have 1 neutron in its nucleus. And we call this hydrogen 2. You can see this here. We have 1 neutron, 1 proton, and then here is the electron. So this is hydrogen 2. Hydrogen 1 is the normal form of hydrogen, or the standard, or maybe just the most common form is this hydrogen 1. Hydrogen 2 is a little more uncommon, but these are both stable isotopes of hydrogen. So they can exist and there's not really any problems with them. However, here is the unstable isotope of hydrogen, hydrogen 3, which has 2 neutrons and 1 proton in its nucleus. So that's where the 3 comes from. There are 3 things in the nucleus. But when we talk about instability, we talk about the fact that this hydrogen 3 will only exist for a set amount of time. After that amount of time, hydrogen 3 will actually change into a different element. We call this change radioactive decay. And all elements, or at least all unstable isotopes of elements, will undergo radioactive decay in some way, shape, or form. Let's go back to uranium. We have a few more forms now. We have the original, the one that we saw before, uranium-238, and so that has 146 neutrons, just like we had stated. Uranium-235, you'll see, same amount of protons, so it actually just has 3 less neutrons. And then finally, uranium-236, 144 neutrons. Now, scientists have kind of documented all of this and also how things decay. We mentioned that uranium-238 was stable. Uranium-235, also stable. But uranium-236 is unstable. And so it's this characteristic of uranium that many nuclear power plants exploit. Okay, we should talk about nuclear fission. I think we kind of get the basics of things. So most nuclear power plants utilize nuclear fission reactors, which work like so. They want to take that stable uranium-235 and they actually want to shoot, for lack of a better word, or bombard it with a neutron. So that it absorbs that neutron. And upon absorption, it will become the unstable uranium-236. This will split into lighter elements spontaneously. Once you send the neutron into uranium-235, you don't have to do anything. Uranium-236 will decay, and it does so rather quickly. So uranium-236 splits into lighter elements, and upon looking at the elements, they're krypton-92, barium-141. Well, that doesn't quite add up to 236, so you get an extra 3 neutrons. And those 3 neutrons can then go and find other uranium-235 atoms. And what this can create is kind of a chain reaction that sustains itself. A nuclear fission reactor sets out to control the chain reaction and sustain it over long periods of time. A nuclear reactor controls the chain reaction through several processes, probably the most fundamental being control rods and moderators. So, let's talk a little bit about that. So, uranium-235 absorbs neutrons. Absorbs neutrons and then undergoes fission. Other elements can absorb neutrons without doing anything. They'll absorb a neutron and they're still stable. We've documented much more of this. Some elements capable of doing this include boron. So control rods are built for nuclear reactors where when you want the reaction to slow down, you just dip a long control rod made of boron into the the fuel, and it will soak up or kind of absorb a lot of the neutrons, slowing down the reaction, not letting it get out of hand. So for this reason, control rods are usually sometimes made of boron for nuclear reactors. Now, other elements kind of don't do either. They don't absorb and decay like uranium. They don't absorb and are okay like boron. Others they kind of do neither, and they sort of allow neutrons to simply bounce off of them, not being absorbed. In both the things we talked about before, boron absorbs it, uranium absorbs it. Some elements don't absorb it at all. They just kind of, it gets close and they let it bounce off. And when it does that, it kind of slows down the neutron itself. So an example of this is graphite. And this kind of facilitates and redirects the neutrons so that they can be absorbed by uranium. And so a moderator can kind of increase reactivity. It can increase the amount of fission happening, kind of in contrast to the control rod. Okay, it's time to talk about inside of a nuclear reactor. There really is only two things that can happen. How much the uranium is undergoing fission, I'll refer to that as reactivity for now. That reactivity either goes up or it goes down. All that we do as people is maintain balance. It's at this point we'd like to talk about one of the cases where an accident did happen. This would be in Chernobyl. So for reference, this happened April 26th, 1986. Chernobyl has more than one nuclear reactor, and the accident took place on the fourth reactor, and it's known as a RBMK reactor. There's a lot of different types of reactors that many different countries have developed. They all kind of work off the same principle of fission, but they kind of all have their unique ways of dealing with reactivity. I also want to bring up a few of the people that were in the control room at the time. On April 26th, 3 operators were present that maintained balance. Their names Akimov, Toptanov, and Dyatlov. Their names will become a little bit more clear later on as to why we bring them up. So, reactivity can do a few things. It can increase or it can decrease. So let's talk about a few of these. Well, fuel is kind of needed for any of this, and so if you have more fuel, you have more reactivity. You have more uranium actually going on your fission. You also have the boron control rods. So these are often compared with the thing you can do to kind of slow down, maybe your brakes or your throttle, if you think of this as a vehicle. So, what else do we have here? We actually have cold water. We're going to talk a lot about cold water because it's very, very important as to what was kind of occurring with the Chernobyl power plant. But essentially, you kind of, in the end, want to heat up some water to turn it into steam to turn a turbine. So what you're going to kind of have happening here is you're going to have cold water being pumped into and out of the core. This cold water being pumped in is a coolant, and so it will help cool things down and actually decrease reactivity. But as the cold water heats up enough to turn into steam, the steam actually, by its very nature, increases reactivity. And another way we can think of this is if we increase reactivity, we increase heat. So the steam just increased reactivity, which increased heat, which is going to boil more water and create more steam. So this creates this sort of feedback, this positive spiral, if you can call it that. So just kind of keep that in mind. More steam means more heat, means more steam, and so on and so forth. What else do we have? Oh, well, in fact, based on the nature of uranium, when uranium heats up, it actually decreases reactivity. It seems counterintuitive, but that's the kind of the nuclear physics of it. It's complicated, and scientists have studied this extensively. And so when uranium heats up, it actually decreases the reactivity. Now, another product of the fission that we didn't actually talk about is xenon. And if we think about what we had beforehand, we just had krypton and baryon. So where does this xenon come on? And that's going to become apparent in a moment, but xenon is present in the core, and it kind of builds up, and then it has this property of being able to absorb a lot of neutrons. And so much like the boron control rods, this is kind of like a control rod that's just naturally occurs. And so it's able to soak up a lot of neutrons and slow down this reaction. Okay. Now we're going to get into the xenon. It's not even here, but we have some elements that occur here, krypton and barium. And they, in and of themselves, are unstable. So the barium, for instance, will change, and all of this has been kind of documented. Barium will change in about 18 minutes, and it will become lanthanum. The lanthanum will then change itself into, I believe, cerium in about 4 hours. Krypton itself changes in about 1.8 seconds and becomes rubidium. The rubidium changes to strontium in 4.5 seconds. And both of those two things at the end here, these two elements, they themselves are still unstable, so they'll change as well. And throughout these processes, it's xenon will come out of this, and every single time some element changes, it releases that radiation that we would refer to as things being radioactive. And so this radiation that it releases is harmful to life. Our nuclear reactors, however, are kind of designed to trap this and not let it get out. So I hope that this makes sense. I hope it's clear. And we now have to talk a little bit about what was going on at Chernobyl, and essentially the fear, I guess, was, and maybe I'll explain a little bit. We have a nuclear power plant that's producing power, and part of that power actually goes into the pumps pumping water into the core. And this is a really important aspect of a nuclear power plant, and so you wouldn't want the pumps to fail. And so they're kind of testing, okay, if the pumps were to fail for whatever reason, for instance, a power grid failure, being unable to supply electricity, and the pumps fail. Okay, what are we going to do? Well, every nuclear reactor plant has this button. It's a very important button, but they can kind of shut everything down. It's called a scram button, and they'll shut everything down. And what this scram does is actually dips all of the control rods into the core at once, and just really, really shuts down the reaction. So, if the power grid fails, press that button, everything will be shut down. But by its very nature, all the things like krypton and barium are still going to undergo decay, radioactive decay, and this will produce heat. So you need to keep water pumping into the core because that heat will build up over time, and you do not want this to happen. This is what's known as a nuclear meltdown. So you gotta have the pumps still running, but the electricity's down. Well, this was thought of, and so what also exists are diesel generators. And so if the power grid fails, you gotta fire up the diesel generators, and they'll pump water into the core until the power grid's back up, essentially. You can keep those running indefinitely until the power grid comes back online, or until that kind of extra radiation from all the elements decaying is gone. And that takes about 24 hours. So if you can run the diesel generators for 24 hours, everything should be okay. So what they were trying to do at Chernobyl was test, in a way, what happens when the pumps are shut off, and could they run the pumps they're trying to test if the electrical grid is shut off from the pumps and the diesel generators take a little bit of time to kick in, could they run the pumps off just kind of the turbine turning for a time? And this was the entirety of the test. So one of the things to note is that they want to do this at a low power. So they've lowered the power for a long time, and that's kind of where we're going to start. Normally, it's supposed to produce around 3,000 megawatts. However, it's kind of running quite a bit lower. It's running at about 30 megawatts. So the power is much low, and that really references the reactivity. It's cold. And so, yes, you have uranium, so that's increasing reactivity. You have the control rods in, you have the cold water that's kind of being pumped. They're not quite ready to shut that off yet, and you have xenon built up. But the power is very low, the reactivity is very low, so you don't really have a lot of steam going on right now. And in order to do this, you kind of have to have a little more power. So how do you increase power here? How do you increase reactivity? And so you start pulling control rods. The operators at the time of the 211 control rods pulled over 200 of them, completely out of the core. So the control rods are gone. Next, as the control rods went away, the power went up, so the reactivity is going up because you don't have the control rods to decrease it, and so they're ready for the test. and they shut off the pumps to the water. So there's water still in the core, but it's not continually being provided anymore because the pumps are now shut off. Next up, the reactivity increases. So any water that was in the core is beginning to turn into steam. Steam increases reactivity, evaporates more water, increases reactivity, and slowly but surely, the xenon, due to the increased reactivity, begins to burn away. It starts to absorb more and more neutrons because the reactivity is increasing, and it slowly goes away. And perhaps you see the state of things at this point. The control rods are all pulled out. There's no water pumping in. Immediately the power level starts to rise because the reactivity is, as we can see here, unchecked. And it is at this point that that things are starting to go a little bit not according to plan, to say it like that. And when things aren't going according to plan, you're starting to maybe think that things aren't going to go well here, which by what we can see is not the case. You press the scram button. Every nuclear power plant has a button of last resort that you press to shut everything down. And this button was pressed. And it had an unforeseen effect. You'll notice I've drug in the control rods to increase reactivity, and this is going to take a little bit of an explanation. But the control rods, unfortunately, did not act. The scram button gets them all in at the same time, and that caused an unforeseen, some might say, unfortunate effect. Here's our control rods. The control rods, I hope you understand here what the image is conveying, but the green represents the uranium fuel, and so it's kind of in these columns, and then you dip the control rods in and out to control things. But not only did pulling the control rods out take away the boron, but it also, on the other end of the control rod, you could say, is graphite, and graphite is a moderator. And so this has all been present when we talked about over 200 control rods being pulled from the core. And so what we have to look at is what's going to happen when you try to insert the control rods back into the core. Well, it's going to look like this. For even just a tiny amount of time, it's going to look just like how I have here. And essentially what was in between here and below beforehand was water. And you just displaced water with something, you just displaced any water that was left, which decreased reactivity, with something graphite, which essentially increases reactivity. And all around this bottom of the core, the reactivity, all around here, the bottom of the core, the reactivity increases exponentially. Any water left turns into steam. It does it so quickly that actually it ruptures the control mechanism here. It ruptures the channels, and the control rods and the graphite get stuck in place. So the one thing you kind of had to decrease reactivity is unable to do that. And the reactivity is skyrocketing. This is designed to run at about a few thousand megawatts. The last reading they had was over 30,000. The reactivity was skyrocketing. And now we have to talk about any water that actually remained in the core flashed into steam. And it continued to heat up. What happens next? You just have to talk about grade 7 science, junior high science. The hotter something is, the more space it takes up. And the core is a confined space. So the steam's heating up and it's filling up the space that it can. And as it wants to expand more and more, as it heats up more and more, and nothing's preventing that heat up. Nothing's preventing that. And so it's exerting more and more pressure on its confines, and eventually pressure wins. And the lid of the core is thrown off. What I've just described is actually just an explosion. Once the lid blows off, the oxygen actually rushes in and kind of combines with the superheated graphite and causes a fire. That fire produces smoke, and the smoke spews radioactive material into the surrounding area. The closer you are to the plant, the worse radiation dose you receive. Radiation is harmful to life. Here is a little, if you recognize the map, this is a map of Europe. Maybe we'll just enlarge it here. Here's a map of Europe. And this is the radiation cloud. Okay, so in the beginning, it wasn't well known what was happening, but there was a fire, so the fire department got called. And although it's kind of vague, the numbers here, we do know that a lot of the first responders including the firefighters, actually died from what's called acute radiation sickness. This is not a process that takes very long. Some of these firefighters died just 2 weeks later. Their gear, actually, you can see that it's still actually in the basement of the power plant and cannot be removed. It's very, very radioactive. Okay, so what do we do now? Well, we have to cover the core back up. And they're thinking about that right away, then and there. It's not a bad idea, but how is very important. In the cleanup efforts that followed, you couldn't actually stand on the roof of the building above the core without being exposed to a lethal dose of radiation for even 5 minutes. They tried robots, but very quickly the radiation ate through their circuits and the robots also failed. The 3 people in the time at the control room, if you recall their names, 2 died within 2 weeks, the other sometime later, 9 years later. Each death attributed to radiation sickness, or just radiation in some way, shape, or form. Just a clarification, when we talk about radiation, it's actually present in far more places than you think. You're exposed to it every time you get an X-ray, every time you fly in an airplane. It's actually even been measured that if you live in a brick building, you are exposed to a measurable amount of radiation. However, that radiation that perhaps comparable to the workers at the nuclear power plant in just is around 500,000 times the amount that you would be exposed to living in a brick building. So amount is important here. And the amount is important, and also the time in which it happens. And everything at the Chernobyl nuclear power plant happened very, very quickly for those exposed to high doses of radiation. So, eventually, figured out a way to do this. The core is covered in time. However, the radiation eats through the metal in some way, shape, or form over long periods of time. The most recent one, the new safe confinement for reactor 4, was installed July 2019 and is designed to last 100 years. They actually couldn't build it. It's over the reactor right there, but they had to actually build it away from the reactor and then slowly move it over the reactor over time. Okay, so that's we're leading up to the end of this. I hope that we have a good indication of how the nuclear power plants worked, and then also what actually happened in one of the accidents. Another reference we'll make is there have been very, actually few nuclear reactor or nuclear power accidents. The technology has been around for over 50 years. And really, even off the top of my head, I can only think of a few, including Chernobyl, Fukushima, 3 Mile Island. And there are very many nuclear reactors around the planet. We talked a lot about what goes wrong, and there's a lot of, because of what goes wrong, a lot of rethinking safety and the safety standards surrounding nuclear power plants. I also hope that this is a little bit of indication on how it affects life and nature, in terms of some of the direct causes and some of the more kind of long-term ones. There's also exclusion zones around some of these accidents, and there's really no one that lives there. However, I'll have you kind of look at the podcast on Fukushima, as well as some of the pictures of the exclusion zone that exists there. That's all.